Good afternoon, everyone. I am Ziqian from the University of Hong Kong. Today, I'm truly excited to share with you a system we tackle one of the most pressing challenges in cloud network monitoring. Our paper is called Skyline, a cloud-centric internet monitoring engine. This is a collaboration between ByteDance, the University of Hong Kong, and the University of Michigan. Here, we have our cloud infrastructure. Two data centers, A and B, connected via an inter-data center network, each with their own subnets. Traffic exists through a POP, which is our gateway to the outside world. Once traffic leaves the POP, it enters the public internet, navigating through BGP routing with the primary AS path under normal conditions and a backup AS path when things go wrong. Finally, on the other end, we have our clients spread across different regions, each with their own client endpoints and CDN nodes. And this entire path from the data center all the way to the client is what Skyline is designed to monitor. So how significant is the problem? Data shows that 63% of network incidents occur within the public internet segment. Even more alarming is that among all several PO and P1 level incidents, 78 are related to the internet, and in 2025, the Skyline system has actually helped us to detect over 2,000 such events. However, monitoring this end-to-end link faces a massive challenges. This is primarily manifested in three ways. First, invisibility. As cloud providers, we have no control over the public internet, nor can we access ISP switch logs or internal signals. Second, scale. The internet comprises approximately 200,000 ASs with a constantly changing topology. Third, diversity of faults. Failures ranging from physical fiber cards to BGP hijackings, and even subtle routing policies errors, making them diverse and unpredictable. So, to address the challenges, when designing Skyline, our core question was, in an internet environment that we cannot control and whose internals are invisible, how can a cloud provider achieve high coverage monitoring of network incidents? To answer this question, we split the problem into three control coverage dimensions. First, traffic direction. We must cover both outbound and inbound directions simultaneously. Second, incident life cycle. Monitoring shouldn't stop at detection. It must cover the repair detection phase. Third, tenant granularity. We need to move beyond simple connectivity checks and drill down into L4 to L7 tenant level metrics. Let's dive into the first question, traffic direction. Why is outbound probing insufficient? The classic example is a unit direction BGP hijack. If an attacker hijacks the route from the client to the cloud, the inbound path, the traffic is diverted. However, the outbound path might still follow the normal route. In this case, if you only ping from the cloud, you will receive a reply. You might mistakenly believe the network is fine, while in reality, the user cannot access your service. Thus, inbound probing is indispensable. We made a challenge. How to cover cloud and client efficiently and non-intrusive. Probing cloud VMs directly is risky and typically not permitted. Our solution is to deploy programmable P4 internet gateways. When an external probes packets arrive, the IGW interprets it and replies directly, without the packet ever reaching the backend VM. This is not only protects the tenant privacy, but also achieves 100% coverage of cloud subnets, enabling truly non-intrusive inbound probing. Let's dive into the second dimension then, incident life cycle. This is a process when meeting an internet incident, not internet incident, every network incident. Once the primary AS path experiences link failures, traffic is automatically rerouted to the backup path. However, backup paths usually offer suboptimal performance. So as soon as the primary paths are repaired, we want to switch back for better quality. Therefore, after rerouting, we must continuously monitor both the current used backup paths to ensure they remain healthy and the original primary paths to detect when they recover. This is demonstrate that full lifecycle management, covering both incident detection and repair detection, is an essential coverage dimension for internet monitoring. Next, to monitor both primary faulty paths and backup paths, we propose FlexPath. Its goal is to solve the flexible path steering problem I mentioned earlier. We leverage segment routing technology, which allows us to ignore standard BGP routing and force prop packets onto a specific path. The process consists of 3 stages. Stage 1 encapsulates the packet with the MPLS tunnel from the data center to the specific edge POP. Stage 2, at the POP, we use segment routing to force the packet into the specific ISP instance. Stage 3, the packet enters the internet and reaches the target. In this way, we can not only obtain the real-time RTT, but also packet loss data for fault paths, allowing us to detect repair signals immediately. Okay, then let's dive into the third direction, tenant granularity. Internet incidents often go beyond simple L3 ICMP ping checks for connectivity and require upper layer information to assist with monitoring. As cloud provider, often the internet connectivity is fine, but the tenant claims my application cannot connect. This frequently leads to finger pointing. The tenant blames the network team, and the network team blames the application. We need the capability of the self-attestation. For example, consider a cloud security devices that erroneously send TCP reset packets. In this scenario, SMP pings might pass through successfully, making the network appear green. However, the tenant's TCP connection are being terminated. This requires us to have passive traffic analysis capabilities to capture these silent killers. To capture upper layer per tenant information, non-intrusive, we propose Flow Hunter, which can trace such signal in a passive and no overhead way. First, traffic splitting. We use optical splitters to duplicate traffic to analysis without impacting production. Second, loading balancing. Traffic is distributed across servers at the TOR level and across CPU cores with each server while keeping per flow consistency. Third, flow tracing. We aggregate traffic with tenant level metrics such as RTT, TCP flags, SMP anomalies, and packet rates. At the physical layer, we use the optical splitters to duplicate the light signal. One copy continues along the normal business path, and the other copy is sent to our DPDK analysis cluster. This achieves true zero overhead monitoring, allowing us to analyze the TCP state of every single flow in real time. In summary, to address these challenges, we designed Skyline. It consists of 3 core subsystems, mapping to the 3 dimensions I just mentioned. First, ByteProp is responsible for high coverage direction and active probing, and FlexPath is responsible for lifecycle management of faulty paths. And third is Flow Hunter is responsible for tenant level passive traffic analysis. Regarding to the evaluation, we validated the system based on 2 years of production states. Skyline demonstrates extremely high accuracy. For verified incidents, our recall rate exceeds 99%. Simultaneously, the false positive rate is really low, with precision reaching 97%. This proves the system's robustness in handling the complex internet environment. The development of Skyline can progress our understanding in cloud-based internet monitoring evolved. We began with outbound probing, a widely used technique for internet diagnosis. Although effective for detecting client-side issues like unreachable IPs due to the ISP outages or link failures, it does not scale up to the cloud side. As cloud subnets increases, ensuring the reachability become essential. So we introduced the inbound problem via AGW programmable switches, enabling agentless cloud subdomain monitoring. The first case is that ISP configuration changes introduce various routing issues. From the outbound probing, everything looks fine. Probers in subnet A see near zero packet loss to multiple regions. But inbound probing tells a different story. Probers in region A observe high packet loss while reaching the other cloud subnets, indicating they are actually unreachable. With ByteProb, we can effectively and promptly detect this issue. Then, we observe that ISP-provided incident and repair information is often unreliable or delayed, hindering timely recovery on primary paths. This motivates us to continuously monitor both faulty and normal AS paths throughout the incident lifecycle and to develop a flex path steering mechanism. The second case, here we show data from a typical incident timeline. ByteProb confirms the fault at minute 15, and the system switches the backup path. Most crucially, flex paths detect the path repair at minute 31, allowing us to switch back to the primary path at minute 41, significantly faster than waiting for an ISP notification. Finally, as the number of the tenants continues to grow, we are overwhelmed by a large volume of tenant reports claiming internet outages. Finer-grained tenant-level traffic visibility becomes essential for accurate tenant-level incident detection and self-attestation of tenant reports. The third case, we can see that Flow Hunter often detects anomalies via TCP reset storms in very early stages. And at the same time, the TX and RX degraded, so we can easily find the problem of the TCP reset. This is caused by a misconfiguration of a security device. Another operational lessons are ByteProb and Flow Hunter are complementary. ByteProb is responsible for quickly identify L3 connectivity issues, while Flow Hunter dives deep into the L4 to L7 application diagnosis. Additionally, we found that POPs with a single ISP and revenue-sensitive regions must be given the highest monitoring priority. In conclusion, our key observation is that existing system lacks sufficient coverage in 3 dimensions: fine-grained bidirectional reachability, incident lifecycle management, and per-tenant upper layer analysis. To address this gap, we introduced Skyline, which provides a specialized subsystem for each dimension. Skyline has been deployed in our production environment for over 2 years and has proven effective in identifying a large number of internet incidents with high accuracy and low overhead. Thanks.